Right, ladies and gentlemen, welcome to the Geological Society of London and to this, the fourth 2016 Society London lecture entitled The Water Book. My name is David Shilston. I'm a past president of this society, and it's my pleasure to introduce to you today the author of the Water Book, Alok Jha, science correspondent for ITV. Water may seem to be the most extraordinary of liquids as it pours from our taps or rains from the sky. But it is a profoundly strange substance. It bends the rules of chemistry and defies easy scientific understanding. Without its anomalous behaviour, however, none of us, and indeed no life as we know it, could exist. As a science reporter for The Guardian between 2003 and 2014, Alok broke dozens of front-page stories, reported live from Antarctica, floated aboard a zero-gravity flight with the European Space Agency, had his genes sequenced, hung out with daredevil botanists in the Lebanon, and reported from Cape Canaveral as the space shuttle took off on its final mission. He is now at ITV News, and his recent book, The Water Book, whose publication only just failed to coincide with our year of water, promises to change the way we look at this essential substance, showing how it has shaped life on Earth, and connects us all to the birth and death of the universe, no less. Ladies and gentlemen, please welcome Alok. Good luck.
Good evening, everyone. I'm just going to pour myself some water from the start. Well, thank you all very much for coming along this evening. So, as I've already been introduced, I'm a science journalist. My background's in physics, and so writing a book about water, which is in many respects a book about chemistry and geology and astronomy and all these other things, is way outside my normal comfort zone. But that's exactly what my normal job involves, so this is why I enjoy doing it, is to learn as much new stuff as possible. And water, it turns out, is the largest of canvases on which to draw the human story. Now, my story is about an extraordinary substance, which I hope that I will leave you thinking about by the end of this talk. But obviously, this is something that we're all completely familiar with in one respect. You probably you've interacted with water in multiple ways, more often today than any person you actually care about or love, or even people you hate. You probably have interacted with them more than you think about how much you interact with water. No, vice versa, that's what I meant. You probably interact with water more than anything else. The point is, we just don't think about it very much. We just don't think about all of the water underlying our everyday existence. You might think about what you shower with or brush your teeth with or you might drink, but actually there's water in everything around us. Everything has a water footprint, and it's mostly invisible to us. So I want to try and bring that substance out, and I want you to look at it with new eyes. My story starts, however, on a much more personal journey. I decided a few years ago to join an expedition to Antarctica. It was something that I'd been offered by a scientist, a friend of mine, who works in the University of New South Wales in Australia. And he was recreating an expedition, a famous expedition from 1913. 100 years later, he wanted to recreate it. And it was an expedition led by this gentleman. Does anyone know who he is? I heard someone say his name. Douglas Mawson. Not many people seem to know. Douglas Mawson geologist himself, and he decided in 1913 that he wanted to find the money for a trip to Antarctica. He is lesser known than his contemporaries, so Shackleton you've heard of, Scott, Amundsen. These people are in the history books as the people who've opened up Antarctica, and Mawson was one of their number. He stands shoulder to shoulder with them. In fact, he went on an expedition with Shackleton in 1909, 1910 didn't quite reach Antarctica, but they did a lot of mapping of the Southern Ocean. In 1913, he decided he wanted to do his own expedition, and so the Australasian Antarctic expedition was born. And he raised money privately and went to Antarctica to map it. He was less interested in racing to the South Pole and more interested in mapping the continent, looking at weather patterns, looking at ocean currents, looking at the wildlife, how it all changed as people got down to these wastelands, essentially. So in 1913 he set off, and here he is in his finest garb. Look, I mean, I have to tell you, we'll talk more about how much of a hero he was in terms of how hardy he was. But having been to Antarctica and seeing him wearing these things, I think, goodness, I mean, like honestly, I had to wear this, and that was like 14 layers of stuff. My point is that I'm not really an outdoors person at all. I don't like being outdoors that much. I don't like walking in the countryside particularly, anywhere where there's uneven ground, anywhere where there isn't Wi-Fi pretty much. So, I'm pretty much stuck in zone 1 in London, if I'm honest. I'm comfortable here. This is all right. But anywhere else that I just don't find very easy because there's no coffee and there's no easy access to the internet and stuff. So I don't like that. But, when you're offered an opportunity to go to somewhere like Antarctica, you've got to push yourself out of your comfort zone slightly. So I got some technical fabrics. I wasn't going to dress like Mawson. There's no way. I don't like being cold as well. I forgot to tell you that. So I got dressed up, and we in December 2013, I was face to face with the ship. We were setting off from New Zealand, so I was face to face with the ship that was going to take me to Antarctica with about 50 or 60 other people, and half of them scientists, half of them volunteers who paid to be on the expedition themselves. And the ship was the Academic Tchaikovsky, a Russian polar vessel. It was been to the North and South Pole, northern and the Arctic and the Antarctic rather. Hadn't been to the South Pole. You can't sail to the South Pole. But had been to the Arctic and the Antarctic many times. So it was a polar vessel, really rugged. And I'd never really been on a ship before. That's another thing I hadn't mentioned. So this was kind of exciting, actually, in the moment. I was sort of standing there, tweeting away the last bits of mobile phone connection. And within 20 minutes of being on that ship, I realized that something wasn't quite right. And this picture, this is the ship itself, will tell you why. If you look at the horizon on that picture, it's quite something, isn't it? And this is what the ship was doing within a couple of hours of us leaving port in New Zealand. And it carried on doing this for days. 10 or 20 degrees each side. And it doesn't sound like very much at all, but when you're in that, it feels like you're going horizontal. But I knew that something was wrong 20 minutes into the expedition because my brain and body just weren't matching up with the senses. Like I was seeing everything relatively calm, but suddenly I was feeling my legs constantly having to balance themselves, and my middle ear wasn't quite seeing. Nothing was stable inside there. It was just something odd. It was as if my body was sort of rebelling against everything I was looking at, and immediately, obviously, I got seasick. It's a horrible feeling. It's disorienting. It's terrible. It's hard to predict who it's going to affect. Experienced sailors get seasick, and people who've never been to sea before don't get seasick. It's impossible to predict. And I had some seasickness pills with me, which I'd taken before getting on the ship. You're told to prevent rather than try and cure it. So I'd taken them a few hours before. Obviously, they hadn't been working. And the pharmacist in Invercargill in New Zealand had said to me, here's some backup ones. These are really strong. Make sure you don't take these until you've been really unwell for a few days, because this is it. This is your final backup. I took those within 2 hours of being on the ship. I was thinking as I lay, sort of fell asleep that night, because within a couple of hours I took the pills and I thought, this is too much. I must go to sleep or try. I remember sort of drifting off to sleep, thinking I've got a month aboard this thing, and I want to get off right now because there's nothing more horrible than this. It wasn't just me, of course. Lots of people got seasick, and it's a very weird thing. But I want to tell you a story about someone else who got seasick. Douglas Mawson, who I showed you earlier, he was not only a great explorer, has one of the most harrowing stories of Antarctica that you may or may not have heard of. And the stories that we hear of Scott, of course, dying on his expedition to the South Pole are tragic and moving. Mawson had his own horrific story. When he got to Antarctica in 1913, he built a base. As it happened, it ended up being in a place called Commonwealth Bay, which is where they landed. And unbeknownst to him, it turned out to be the windiest place on Earth. And so it was already looking bad for his expedition. The average gusts, apparently, the average wind speed for his 2-year stay there was something like 90 miles an hour. And gusts went up to something like 150, 200 miles an hour regularly because of the geological formations around there. The katabatic winds of that particular area meant that the wind from the polar plateau just fell down these mountains straight onto his base. So he wasn't very lucky. But anyway, he built this base there, and then he split his group up into teams of 3 and sent them into Antarctica to map the continent, trying to join up the maps with what Scott had done earlier. And his team consisted of him, and in front of him, they would ride on sledges in a single file. In front of him was Xavier Mertz, who was a Swiss ski champion, and behind him, a British Army officer, Belgrave Ninnis. And the 3 of them, when they got to Antarctica, had been going for weeks and weeks into the centre, mapping everything they could see, taking weather measurements, looking at the life or lack thereof around them, and recording it all. And really good measurements, by the way. And about 5 weeks in, Mawson writes in his diary that that going along, and Xavier Mertz stops in front of him and turns around and is pointing over Mawson's shoulder. So Mawson sort of wonders what's going on, and he looks over and he sees that there's no one behind him. And they wonder, where's Belgrave Ninnis gone? So they sort of walk back carefully, and they see a hole in the ground. And at the bottom of the hole, there are some bits of sledge. They can hear some dogs making a whining noise. And they call down. They call down and they call down, and there's no response at all. There's no response. And they've lost Belgrave Ninnis. And he's their friend, a close friend, a fellow explorer. So obviously Xavier Mertz and Douglas Mawson are both heartbroken. They don't know what to do at this point, because another stroke of bad luck has meant that that what they'd done was to split their provisions up between the 3 sleds, and they put most of the food and the best dogs on that final sledge, because they obviously, like any of us would think, thought that final sledge would be the last one to go down into a crevasse. So they'd lost most of their food. They'd lost their best dogs. They were 5 weeks away from their base. And they also had to get back, on a timetable, because the ship that had brought them to Antarctica, the Aurora, had to leave the Antarctic coast by about February. And this was late December, early January when all this was going on. So they had to leave Antarctica in February. And because the Antarctic winter would then draw in and it would trap the ship, and they had to get out before then. So Mertz and Mawson decide to head back. Within a week of their duo trek, they've run out of food, so they start to eat their dogs. A few days later, Xavier Mertz falls into a fever, and he's shivering, he's getting seizures, and unbeknownst to him, what happened was that because they've been eating the dogs' livers, it turns out, have a lot of vitamin A. If you eat too many dogs' livers, you get poisoned with vitaminosis. He was being poisoned, and he died in Mawson's arms. So at this point, Mawson's by himself. He's still several weeks away from Commonwealth Bay, where his base is. He carries on by himself, falls into a crevasse, and sort of manages to climb out, and then cuts up his sled and builds a sort of system of ties it onto his back, so that if he falls down another crevasse, it would sort of trap along the top and he can climb himself out. And he falls down several crevasses like this, but always manages to crawl out. He writes that in his diaries that his feet fell off, the soles of his feet fell off every day, and he had to reapply them with lanolin and bandages. And obviously, his health was not great at the time as well. Despite all of this, by the way, he carried on making weather measurements, such good weather measurements that they're still quite good baseline data for that part of the world today. So he was a scientist. He was a very, very good scientist. He carries on walking, falling into crevasses, having these enormous problems, and gets to a point that's a hill, which he knows overlooks his base. It's 5 kilometers away at this point. And in that base, the expedition teams had stored fruits and all sorts. And it meant, and when he got there, he saw pineapples, he saw oranges, and he was overjoyed because he knew that meant that there must still be people at the base waiting. And also it meant it was the first time he'd seen any colours for several weeks, because everything was white around him, obviously, until then. So he sits there, and a blizzard hits at the same time. So he's stuck in that cave for 4 or 5 days. They nicknamed this thing Aladdin's Cave, by the way. So he was stuck in Aladdin's Cave for 5 days. And when the blizzard cleared away, he left, walked down the hill, and reached Commonwealth Bay, where his base was. The people emerged from the hut. They saw him. He was bedraggled. They weren't sure who he was. They weren't sure what would happen to his 2 colleagues. And he was obviously incredibly weak. And as they welcomed him back, Mawson noticed on the horizon, he noticed a puff of smoke. And it was the Aurora, his ship, and it had left that morning. So he was stuck in Antarctica for another year in the hut, in the windiest place on Earth, because of his various travails. Now, my point in telling you that story is that it shows you what kind of man Douglas Mawson was, why he deserves that place as one of the explorers, the real explorers of Antarctica. He was obsessed with the science, he was obsessed with recording these things, work that carries on to this day. He led that, he began a lot of that work. And he wrote a meticulous diary, and the story that I just told you is in that diary, and he wrote constantly. But his diary is conspicuously empty for the first few days when he left Australia. So when he left Australia, he was travelling across the Southern Ocean, it was empty. And that's because his diary was empty because he suffered from extreme seasickness. Now this man, who did all the things I told you, even he suffered from seasickness, is my point. Now the reason me and Mawson, if I can say it that way, suffered from seasickness, and many people have done since, is because the Southern Ocean at those latitudes, 50 and 60 degrees south, there's no land all the way around. So the winds can whip up all the way around the Earth, and they get to enormous speeds. And the fishermen and the whalers and so on used to nickname those winds the screaming 60s and the furious 50s. And these winds have destroyed many a ship. Fortunately, our ship was very, very strong and it didn't get destroyed. But it did cause it to roll around and just get tossed around as if it was nothing. And it was my first experience of thinking, realizing, I suppose, we all know this, of course, but realizing just how powerful these forces of the ocean are. If you looked at the Earth from space, you would see it as a water planet. I mean, it's 70% covered in water. And you would think it's a water planet with a few non-watery bits in it. We sort of surround ourselves with land and cities, and we've controlled our environment to such an extent where we use water, but we get annoyed when there's rain or whatever else. But for most of the Earth, water is the environment, and water in the atmosphere, water around you. It controls everything. The Earth is a water planet, and we've known that, of course, since we've been mapping the Earth or whatever. But even humans, the very first humans, knew that water had something special about it. If you go back to any creation myth or story about a cultural story about how the world might have appeared, it always involves some sort of water. In Genesis, God moves above the still waters to create the heaven and the earth. In religions such as Hinduism, Islam, and others, you cleanse yourself, and there are demons or other gods that live in these waters. So, in every culture, there's been an attempt to understand or mythologize or venerate water in some way. And only in the last few hundred years have we tried to actually access this material using science. So we're kind of, as scientists, late to the party on that. Water has something that has been fascinating to people for much, much, much longer. What I like about the myths is this, and the stories. I'm a scientist, so I don't believe necessarily that those things are true. But what I love is the sentiment behind them. They make water something heavenly, and in one sense, they're absolutely right, because all of our water on the earth really did come from the heavens. It came from space. To understand where the source of our water is, we have to go right back to the beginning of the universe. Water is H2O, 2 hydrogen atoms, 1 oxygen atom. And all of the hydrogen that we know of in the universe was created a few minutes after the Big Bang, 13.7, 13.8 billion years ago. For the first few minutes, you can imagine it was incredibly hot. Nothing particularly interesting happened in that time. And then within 3 minutes, the universe had expanded enough to create the first particles, and these particles interacted with each other. And a hydrogen atom is simply a proton and an electron that are bound together electrically. And there's your hydrogen atom. Most of the universe at that point was just hydrogen atoms. And as the universe expands, it does so in a very sort of it doesn't do it in a smooth way. It does it in a very clumpy way. And wherever there are huge clumps of hydrogen, big clouds of it, the hydrogen would have collapsed through gravity and formed the first stars. And those stars shone for several million years. At the centre, the hydrogen was being fused into helium, and when all the hydrogen was fused in the centre, the helium was fused into higher elements, carbon, nitrogen, etc. And this went on until it couldn't fuse anything anymore. At that point, the star exploded, and we've seen these objects in space, and they're some of the most beautiful things. This is the Helix Nebula, 700 light years away, and it's 2.5 light years across. And what you're seeing here is the remnants of a star that's exploded. Then it's not a real colour image. The colours indicate different elements, and it's been coloured just to show you the distribution of those elements. But it's 2 light years across, and inside there was a star, and what you've got left is the dust, the ashes of that star. Here's another one, the Rosette Nebula. This one actually is enormous. It's 50 light years across. It's 5,000 light years away. And probably one of the most famous nebulae is the Horsehead, Pillars of Creation, the Eagle Nebula. It's 4 light years across. Now these beautiful things, this is the nursery for our water. In fact, it's the nursery for our whole solar system. In a nebula, probably similar to one of these, that's where the sun was created, or the sun formed itself. So in these clouds, I told you there's all sorts of stuff that created in the centre of the first generation of stars. But there's still lots of hydrogen, and that hydrogen will, when the time is right, when it gets clumpy enough, will attract each other through gravity and form another star. And our sun formed in a nebula like this 4.5 billion years ago. Now, as it took its first birth cries, if you like, started to shine, the material around it obviously was affected. If it wasn't sucked in or pulled in by gravity, then around it would be warmed, or the gravitational influences of it would make the dust sort of start to orbit. And that dust is where our water is formed. So in that dust, if you can imagine, very, very empty space, and in 1 centimetre cubed or so, you might get a few particles. That was enough for the formation of water. What happened? Well, in that dust, there was little tiny grains of carbon, so, nanometer size, 1,000th the width of a human hair. Tiny, tiny grains of carbon that had been formed inside the stars and exploded. And they were just floating in space. And occasionally, a hydrogen atom might bump into that thing. Occasionally, an oxygen atom might do the same thing. And usually, they'd just bounce off and go back into space. But sometimes, hydrogen and oxygen would bounce into the thing at the same time, and they would fuse into a molecule of water. And there you have it. That's where our water came from. Molecule by molecule, over hundreds of thousands of years, each one of those carbon grains was coated in ice. And most of the time, the ice would just shatter off again and go back into space. But a few and enough of those grains eventually would come together to form stones, and those would come together to form boulders, and the boulders would come together to form the building blocks of planets. And we start to see the rocky planets and beyond forming from these grains around the sun. The Earth, 4.5 billion years ago, wasn't a pleasant place, however. As it starts to form, it's covered in there's lots of volcanic activity, there's a lot of energy being released to the surface because all the rocks are coming together, and a lot of the water that was on the surface at the time just evaporated away. The atmosphere wasn't, dense enough essentially to trap the water that we would now enjoy. So all of the surface ended up being quite dry, and this period, the Hadean, named after the Greek for hell, although you're a geologist, so I wouldn't have to tell you that. That time, it was incredibly dry and unpleasant on the surface of the Earth. So whilst the water had been created in the solar system, it exists on these grains, and these grains had created the planets, it was all driven away again because of the way the Earth was formed. But obviously we have oceans on our planet. We are a water planet. So where did that water come from? Well, not all of those grains that I talked about earlier ended up forming the planets. A lot of them ended up forming asteroids and comets and other bits and pieces that ended up at the outsides of our solar system, beyond the orbit of Pluto. Places like the Kuiper Belt, a region of sort of relatively unknown space that contains an uncountable number of objects, detritus essentially from the formation of our solar system. And at some point 4 billion years ago, so this is 500 million years after the Earth had been formed, and we were living in essentially a hellish land. Well, we weren't around. But the Earth had this hellish landscape. 4 billion years ago, something disturbed the Kuiper Belt or beyond, and huge numbers of asteroids and comets from that region of space made their way towards the Sun, and for 500 million years, our planet, and Mercury and Venus, and Mars for that matter, were bombarded with asteroids and comets. It's a period called the Late Heavy Bombardment. And all of those objects that hit the Earth contained some water, and that's where the water came from. So when I told you it came from the heavens, it really does come from the heavens, and it came 500 million years after the Earth was actually formed. So after a week at sea, going back to my Antarctic journey, across the Southern Ocean, the temperature gets colder every day, of the air and of the water, and eventually you start to see the first bits of ice. Here's some pack ice. This is the remnants of the previous year's winter. So every year Antarctica doubles in size as the sea freezes. And then in the summer, the Antarctic summer, it melts and the ice will float away into the Southern Ocean. So we were seeing a bit of this. And this is kind of very new ice, maybe 1 year old, only a metre or so deep, but beautiful. I mean, you start to see colours in water and in ice which you just don't see anywhere else. Also, you see big chunks of ice that you don't see many other places, just floating merrily away, probably going to survive for another few months before they disappear. And as you get closer to Antarctica, of course, the ice thickens up, and as you get closer, you see ice that's maybe 2 or 3 meters thick that survives several winters. It's harder to get through. There's fewer paths all the way through it. I took this picture just to describe one other thing that happens when you go on an expedition like this. And I don't know if many of you have been on these sorts of journeys, but we're used in our everyday lives in cities like this. We're used to controlling everything around us. We see colours and flavours and tastes and smells and things. And when you go to a place like Antarctica, a pure wilderness like this, where there are very few colours, where there are very few smells, all sorts of colours of crystal ice. There's greens and golds and all sorts in there if you look closely enough. And generally speaking, the landscape is mainly white because of the ice. But at sunset every day, and in the Antarctic summer, by the way, the sun never goes below the horizon. It's always light. But around 1 o'clock in the morning, the sun will sort of skirt the horizon and come back up again. And you get this enormously beautiful light show. It's as if the whole of the landscape has been drained of colour But that colour's been stored away, and then it comes back just for those 2 hours in this burst of oranges and apricots and peaches all at the same time. As you get closer to Antarctica, you see the first pieces of Antarctica itself. So icebergs, we're all familiar with icebergs, but seeing one of these city-sized objects in the flesh is quite an epic thing. And this one was about 50 metres tall, probably, and probably had another few hundred metres underneath at the surface. And what this is essentially is this was the first iceberg we saw, and these are pieces of Antarctica itself. Whereas the ice we'd seen up till now, were just the sea frozen and then unfrozen and then melting again. This is actually a piece of Antarctica. This is a piece of a glacier on the land or on the ice sheets of Antarctica. Snow will fall in different seasons, and that snow builds up over hundreds of thousands of years to create monumental blocks of ice, which essentially will creep to the edges, and bit by bit they'll snap off. And this was one of those pieces. I mean, it's incredible to think that this thing has been around for 100,000 years or more. And as they float further out into the ocean, you see how they start getting shaped by the winds and the water. So all of these things are shaped by the winds and water, and each one is kind of obviously unique for that reason. I don't know if you can see here, there's like an ethereal blue light. And that's from light coming into the surface, bouncing around and coming out. Refracted around inside and coming out. So it's got an internal glow about it. It's incredible things. And it amazed me to think that this iceberg, huge as it was probably has probably been around for longer than all of human civilization, and will be around for much longer than any of us. And it's just a small piece of what was to come. And this wasn't the first iceberg we saw, of course. This wasn't the only iceberg, rather. We saw many. After a while, it got embarrassing. There were so many beautiful things, but obviously they're also incredibly dangerous if you get anywhere near them. But these citadels essentially have existed for so long, and they will continue. That is incredible. But perhaps what I found most incredible about it wasn't the age, and it wasn't even the epic size of it, although those are wonderful things. It's how this iceberg gives you a window onto just how fundamentally strange water is. Because what you're looking at there is a solid water ice floating on its own liquid. And there are no other molecules, at least that I can think of, where that happens. Now, we're so used to this happening that we don't think of it as strange. You have an ice cube in your drink, you see a lake freezing at the top, and there's liquid underneath, that's just what happens. But this is not normal. Nothing else does this. And this is our first window into the chemical anomaly that water is. Why does it do it? Well, as water cools down, if you take it at this temperature here, as it cools down, it does actually condense a little bit, not much, and then it gets to about 4 degrees Celsius when it's most dense. After that, when you make it colder, the water molecules start to separate. By the time it gets to freezing point, it's in a particular configuration in the crystal of ice. It's in such a configuration that's actually less dense than the water at the same temperature, 0. It's just weird. Now, this is lucky, because it's not just an anomaly that you think, okay, that's interesting to know, tick it off, move on. If water didn't behave like this, if water didn't freeze and float on itself, if it behaved like every other liquid, then we would not have life on Earth. Because if you think about the history of the Earth, there have been many, many ice ages, where the surface of the Earth has largely been covered in ice, and it's been very cold, very little running water around. And life needs water, liquid water, to survive. If water froze like something else, if it froze from the bottom up, for example, then any life form that was evolving in the early stages of the Earth, anything that was evolving at the bottom of a pond or a river or anything like that would have been completely wiped out. And this unbroken line between the first living organism 3.8 billion years ago and now, all this evolution, all this complexity that we see around us in life, wouldn't have been allowed to happen if you kept breaking the chain every few 100 million years. If it wasn't for the fact that water froze and floated, then we wouldn't have had life on Earth. Now, this is your window into the anomalies. And actually, to let you into a secret, the chemists I spoke to for this book were mostly frightened of water, even the ones that study it. It's incredibly difficult to understand. It's incredibly difficult to study because it's not just a floating thing. There are so many anomalies about it. Ice floating is one strange thing, but really, on the surface of the Earth, water shouldn't be a liquid at all. If you think about how the chemicals, actually, the weight of the chemicals and how similar things behave. And to understand why, look at this. This is a water strider. It's an insect that sits on the surface of a pond and doesn't fall through. And you've probably seen many of these. It doesn't fall through because the surface of the water has such a high surface tension. Water is something that likes to stick to other things, and it dissolves things very easily. It pretty much dissolves anything. And if you don't believe me, then look at the Grand Canyon. It was basically dissolved by water. It just needs a lot of time. But water likes to stick to things and dissolve things and interact with things. But it doesn't like anything more than itself. So water loves to stick to itself. And so in any sort of liquid, like a glass of water or whatever, the surface has enough tension because the water molecules want to stick together, don't want to separate to allow stuff through it. And if you're light enough, like this water strider is, then you can just skate on the surface as if it was essentially a nice trampoline surface or something. Now, this property of water is kind of extreme and strange for a liquid, but it also explains the fact that water, for example, has quite a high boiling point. Because the water molecules like to stick to themselves, they need a little bit more energy than normal to be boiled up and turned into a gas. So if you think about other chemicals that are similar in terms of molecular weight to water, water is H2O. If you think about hydrogen sulfide, H2S, similar molecular weight. Or ammonia, NH3, nitrogen and hydrogen. These things have similar-ish molecular weights, but they're all gases at this sort of temperature. They freeze, they turn into liquids at minus whatever, many tens of degrees below zero. Water doesn't do that. And the stickiness of water is partly the reason. It's because water likes to stick to itself and therefore it needs slightly more energy to turn into a gas. Therefore, at our temperatures, it's a liquid. And the reason that water likes to stick to itself, what's fundamentally underneath it, is because of the chemical, the sort of makeup of the molecule itself. If you've ever seen a water molecule drawn out, it looks like a shallow V. And at the apex of the V is the oxygen atom, and at the two ends are the hydrogen atoms. And overall, this thing is electrically neutral. But if you zoom in, you'll see that the hydrogen atom is just fractionally positively charged, and the oxygen atom is just fractionally negatively charged, creating essentially a dipole. And this dipole is interesting because it basically runs a lot of the things I've talked about just now. It explains a lot of those things and explains pretty much why it's the most useful substance you want if you want to run a life form. But what that dipole does is it allows water to interact with itself and other things in really interesting ways. So the hydrogen atom of one molecule will attract the oxygen of another. Now, and that bond is called the hydrogen bond, and water forms 4 of these things. Now, other similar molecules like hydrogen sulfide, etc., they do form hydrogen bonds too, but nowhere near as many as water. And because water forms so many of these bonds, it sticks to itself. It has a high boiling point, and all of those things happen. Also, it's really useful if you want to run the processes inside a biological cell. Now, we are all 70% water. And we obviously, you drink and eat, drink water and eat it in your food all day long. But I wonder if many of you thought, what is water actually doing inside you? What is the function of water inside you? Well, it does an almost infinite list of things, but here's two important things. Number one, it's making sure that your DNA is working properly. DNA doesn't actually do whatever it wants to do unless it's dissolved in water. That's pretty useful. Number two, it's making sure that every single protein inside your body is the right shape. So when a protein is made by a cell, it comes out as a long chain of amino acids, a sort of floppy chain, and it's useless in that form. It's when you throw that thing into water, it automatically shapes itself into the correct thing that it needs to be. So when a protein molecule is produced, it's long and floppy, as I said, but there are bits on it which like water, and there are bits on it that don't like water. And when you throw that whole thing into the intracellular medium, or inside the cell rather, where there is a lot of water, the bits that like water stay on the outside, the bits that don't like water fold themselves into the middle. And that means you get the right shapes for whatever your protein is going to be used for. And the water does many other things inside cells, but fundamentally, without water, life doesn't exist at all. And it's remarkable to me, actually, and remarkable for part of our story too, that wherever there is liquid water on Earth, there is also life. And it kind of doesn't make sense when you first think about that, because if you go to places like Antarctica, you look at this, you think, this is an extreme environment. There's no plants there that you can see, certainly hardly any life at all. And it's just barren. There's almost nothing there. Of course, it's not really, what you see isn't necessarily what you get, because even though this is all completely dead to life, essentially, there is life here in Antarctica. These are the first bits of life that we saw. Adelie penguins, absolutely beautiful, doing what they do. They live close to the water's edge of the Southern Ocean because they hunt for krill and other plants and things that live at the bottom of that particular part of the ocean. There's my selfie with one. You've got to have one, right? They're lovely, aren't they? I'm just going to keep showing you pictures of penguins now, if you want to show. There are also seals. These are Weddell seals. They hunt at night and then come up during the day to basically sleep all day. Absolutely some of the most lazy creatures I've ever seen in my life. Mostly, that's all we saw. They just all slept all day. So it's a life that we all want to lead one day, I'm sure. Anyway, the point is that life does exist, even in these extremely difficult situations, because, especially here on the edge of the continent, there is liquid water. But actually, if you go further in, there's still life there. We're discovering it all the time. There are lakes underneath the glaciers that have been cut off from cut off from the rest of evolution, essentially, for hundreds of thousands of years. And after drilling through the ice caps into these lakes, we found all sorts of microbes under there in these extreme places. I think it's remarkable. Places like Lake Willands, for example, which has been isolated for millions of years, they found 130,000 cells in a milliliter of water, 4,000 species. In some of the valleys of Antarctica, which are the coldest and driest on Earth, and it's dark for half of the year, you get communities of cyanobacteria and lichens and green algae. Not only here, in hot springs, which, if you think that they're at 100 degrees Celsius, if they're at the bottom of the ocean, hydrothermal vents, life survives there too somehow. It's managed. The hottest place, the most inhospitable environment ever recorded for an organism is there's an archaea, a form of archaea called Geogamy barossi, strain 121, because it lives in water that's 120 degrees Celsius, essentially, 121 degrees Celsius. And also in the Atacama Desert, where it hasn't rained for hundreds of years, there are essentially dormant organisms that whenever there is a light dusting of rain or some ice might melt for a month or two, they'll grab onto it and reproduce. Sorry, more pictures of this. This is There's another penguin. What I'm trying to tell you with all the story about the life forms that can exist wherever there's water, is that it gives you something to think about when it comes to water elsewhere, beyond the Earth, and therefore life beyond the Earth. If life can exist in all these weird places around our planet, and they do, I mean really they do, if there is liquid water anywhere, there is life there. But if there's no liquid water, there is absolutely no life. These are always together. If life has found a way to evolve into all these places, then why wouldn't it also have found a start elsewhere too? Now, we've been looking for water in space for generations, and we know that it exists on pretty much all the planets of the solar system. Even Mercury has polar ice caps made of water ice. And we know that certainly Mars has ice at the poles, it has water locked into the soil as well. But also, as of last year, we know that there's seasonal running water on Mars, like very small amounts. And even beyond that, the moons of the gas giants seem to be essentially balls of ice with oceans underneath the ice. Even Pluto, which is not even a planet anymore, but we're still interested because it's cool, that is covered in mountains of water ice. And we know that from New Horizons last year. The annoying thing about writing a book about water is that every month there's something brand new which you have to put in, and so it becomes out of date immediately. Now, it seems to me that, as we discover these other places, and we find liquid water in these places too, you've got to, the romantic inside me wants to think that these are great places for life. Take this place. This is Enceladus, one of the moons of Saturn. And it's essentially covered in ice and many, many, many kilometers thick. And there are cracks in that ice that are jetting out water. These are geysers. There are someone nicknamed one of these geysers Cold Faithful. And actually now we know that Europa, one of Jupiter's moons, also has similar water geysers coming out. And I think, I may be wrong in saying this, but I want it to be true. I think it's true. Most of the geysers that we know of in our solar system are not on the Earth anymore. So there it is, water flying out. We know that on Enceladus, for example, there's a thick layer of ice. Underneath there's ocean. It's warm ocean, by the way, and it sits on mineral rock. These are the conditions that these are the conditions basically that we think life used to start on Earth. One of the best and most compelling theories about the way life started on Earth is that it happened around hydrothermal vents on the ocean floor. So warm water, lots of nutrients, lots of energy that allowed the other molecules and rocks and other things around to start the processes that would become the first cells, cell membranes, and so on. So if it started here, why not elsewhere? And this, we found a couple of places in our solar system that have sort of oceans of water, but we know there must be oceans on the many extrasolar planets that we keep finding. We found 3,000 extrasolar planets in the last decade, and we find them at an alarmingly high rate. The estimates are there's trillions of these things. Many of them will have liquid oceans, water oceans. And again, if water has been used, has managed to achieve all these things on Earth, i.e. life, and then people like us to appreciate it, why can't they have done it somewhere else? And here's the other thing I like about that idea. Like I said about humans at different times in history, we may not know their culture or their food or their language, but we know how they use water, and they will know how we use water. If we were to find aliens out there, they may use different molecules than proteins or DNA to do their daily, to do their daily growing or passing of information between generations. But you can bet there's a high likelihood they'll use water to make all of their stuff happen. So, just to conclude then, if I asked you to think of a liquid, you're almost certainly going to think of water. Even if you actively think of something else, blood or orange juice or beer or whatever else, it's mainly water with some stuff floating in it. That's all it is. And water is so common that we think of it as completely mundane. Every day we drink it, we wash with it, we wet things, we dry things. It's just not there. It's so common. It's so woven into the fabric of what we do and what's around us. It's invisible. And in a sense, water has made itself invisible to us in that way. And we can only understand the things that I've talked about, the anomalies and all the other things, because we have got the scientific method to be able to stand outside our own experience and to look and examine. But still, it's worth just thinking about what this stuff is for a second. If you've got some water, then just take it out and hold it and look at it. This colourless, featureless, tasteless, but ultimately remarkable material. Without it, none of us would be here. And the more we examine water, the more questions we get about it. And we study it because we're made from it. And, it made us. And I suppose the most intriguing thing about all of that is that the substance that we're made from, that's made our world, is still so mysterious to us. Thank you. Some questions,
Great.
I believe.
Well, I open the floor to questions. We have a roving mic, 2 roving mics, I see.
No questions. I think I've answered everything.
Oh, well, in that case, I was chatting to someone as I was buying your book.
Okay. Yes.
And he said to me, is ice a rock?
Yeah, why not?
Well, we talked about it for about 10 minutes.
It is. I mean, we don't think of it as a mineral, but what is a mineral? It's just frozen other stuff, really, isn't it? Sorry to make it sound make any geologist's entire career and work feel small, but no, that's what it is. It's a crystal of something. So ice is just a crystal. And of course, in our daily experience, it's sort of soft and malleable sometimes, and you can break it, and it's easy, snow and all that. It doesn't feel like a mineral. But the people I talk to who study ice are absolutely convinced that, a sufficient coldness, it is just as rock, essentially. And on the Earth, it behaves like one in many respects, in terms of the sheer physicality of it on places like Antarctica. The fact that it can exist for hundreds of thousands, millions of years and trap history through it in the way that we study rocks to do the same thing. Yes, why not? Let's call it a rock. I only talked about ice 1, by the way. There are 16 types of ice, but ice 1 is the only one that exists on Earth naturally. All the ice we see is ice 1. It's this form that floats above the liquid. Every other form of ice actually sinks. So other planets where other ice types exist, there's no life for that reason. But all the other ices, they're much denser, and there are many more to be discovered as they get denser and denser, and you can create these in labs. And so a theoretical chemist once said to me, well, we keep creating denser and denser forms of ice just to look at and examine, because what you do is you try and sort of pack the molecule in closer and closer formations. And of course, the ultimate formation that would be the most dense for water, if you can force it, is a close-centered cubic structure. And a pile of oranges, basically, if you imagine that. Something like that, if you have the atoms in that shape. And he said to me, if we ever found that, and it might exist in nature, maybe at the centre of stars or something, because you need incredible density, that is basically a metal. So never mind rocks. You can have this stuff in any form you want, basically. We haven't found that one, though.
If the pressure's high enough.
If the pressure's high enough,
yeah.
And it would conduct electricity. So be careful around that stuff. So anyway, yes.
Right, here we go. Gentleman on the... That's it.
Just a follow-up to that question about rocks. Would you describe water as technically a liquid?
Yes, this is a liquid.
No,
What's your-
water can't take pressure, unlike other liquids.
In what
So
way?
how do you define water in that respect?
Well, I mean, I don't know what you mean. How,
It doesn't take pressure. It's very clear.
but it's still a liquid.
Well, that's what I'm asking. I don't,
Well, I would call it a liquid.
I've seen
Maybe
it-
there are more refined descriptions of what liquids are.
I don't think the technical definition of water is a liquid.
What would it be? That's a good question.
It's unique.
It's for part 2 of the book, I think, maybe. But I've called it liquid because, you know, in our general understanding of it, it is for that purpose it's liquid. But as I said, I hinted at, there is obviously in chemistry you've got a theory of liquids which tells you how liquids behave, and water doesn't follow that. It doesn't cover water. So in a sense, you're right. It's not technically liquid, but for our intents and purposes, we're getting slightly psychedelic if it isn't a liquid.
Rightio, there was someone over there. Oh, there we are. Gentleman with the glasses, yes.
Hi. Is water the new oil?
I'm sorry?
Is water the new oil?
How do you mean?
We're fighting over it. We're taking over other people's land to get hold of it.
Yeah.
We're in, whether you go to Jordan or the Omo River.
So you're talking about resource, basically.
Yeah.
So yeah. So in one sense, obviously, it's not, because it's not a fuel in that respect. Although I suppose it could be used to some in fuel.
Okay. Is it the new resource we're addicted to?
Absolutely. So yes, I know what you're getting at, and I think you're right. It is the addicted sounds like a bad word. We need it. There's no getting around it.
I'm addicted to breathing as well.
So well, I would use a different word. But anyway, yes, water is the stuff that is becoming harder and harder to. It's the resource aspect of it is incredibly important, especially as our climate changes and it becomes available in different places. The amount of water on the earth, there's still plenty of it. It's just not available in the right places, and therefore you get these series of conflicts that happen. But then, actually, conflicts around access to water have been happening since the beginning of all settlements and civilizations. The reason you build your city next to a river is because you want access to that river for whatever you want to use it for.
Yeah, I'd argue though that the potable water, fresh water, is actually a depleting resource because of the way we manhandle it and pollute it. So actually, the amount of drinking water is decreasing whilst our
It might well be.
consumption patterns are increasing.
That's right. It might well be, but the thing is that there is still a lot of water around. It's not that we'll run out of it if at some point there's going to be none left. We have to manage it better,
It's in the wrong
and it
place.
makes it more expensive. Certainly. So if you don't do it in the proper way, if you pollute, or if you make sure, if the weather patterns and climate changes in such a way that certain parts of the world where there are many people living suddenly don't have any easy access to it, that creates problems. But I think that that understanding of how important water is in all the materials you have around you, so whether it's this desk or this piece of paper or a computer, each one of these things has a water footprint. It uses water to be manufactured, and most of the water you actually use in a day is not the stuff you drink or eat, it's the stuff around you. And so that's where, all the importing.
Yeah,
of food
it's the embedded water in the products we buy.
That's right. Yeah.
The unseen, invisible.
So
water.
that's the stuff that is really using stuff up, and especially as in the West, we're using a lot more of it than places elsewhere. And if those other places want similar sorts of materials to us, then you can imagine the amount of water they're going to need is going to be enormous. Yes, it's a massive problem. It'll make it more expensive.
I reckon petrol's about £1 a litre. If I go down the shop on this street, I bet water's about £1 a litre or more as well.
I bet you is. I bet you can get water that's much more expensive than that if it pretends to come from a glacier.
From icebergs, nonetheless.
Yeah, that's
actually.
right. Yeah, which is a waste of
Thank
money.
you. That's great. Now,
Sorry.
Oh, here we go. Yes.
Hi there. Great talk. And I like the way that it was almost presented the story as a history, starting 3 minutes after the birth of the universe. But I'm just wondering, in that context, maybe this is the subject of a future book, what's the future of water in that sense? So if you've charted the history in terms of the universe and how water came to be here on the planet and the fusing and things like that, are there any thoughts on, in terms of the mega trends for as far out as we could see, what is happening in terms of? Well,
so it depends how far into the future you want to look. So if you're looking at just humans and life on Earth, the water cycle continues, and will continue for however long the Earth is around, and not too close to the sun. So it will continue for circulating around the Earth. I mean, the same water that we're drinking today was probably in some dinosaur a long time ago, so it's not going anywhere in that respect. In 1 billion years, though, if you want to go that far ahead, the Earth will, the sun will start to get into a phase where it starts to enlarge, and the Earth's temperature starts to get higher and higher and higher, and most of our water will have boiled away at that point. So all the surface water will have boiled away, and it'll be dry. It'll be very hard to live on this planet at that point. So we've got 1 billion years to find somewhere else. We haven't evolved into something else, hopefully, by then. And that water, by the way, which came from space, landed on our Earth, maybe has been on the Earth for 5 billion years, will just carry on, and some of it will go on and form other planets, maybe. Most of it will probably be just disassociated into atoms, because most of the water that's created, when I told you that story about the carbon atoms and stuff, a lot of water is also created when a star forms. All the hydrogen and oxygen around it will react, and whenever you get a star forming, you get these jets of water coming out the ends, huge amounts, like the Amazon rivers every second, coming out of the ends of these things, and little ice crystals essentially fire off into space. But every one of those molecules will be torn apart by ultraviolet radiation that's in deep space. So they just disappear after a while. It's ephemeral. And most of our water will drift off into space, and if it's not caught by something else, like a planet, for a few more billion years, it will just disassociate into atoms. And if you want to look even further than that, well, all the atoms fall apart after that. So, heat death.
I think we will stop there.
Sounds like
knowing we've only got about 1 billion years is a bit of a problem to a geologist, I have to say. So I'd like us all to thank Alok for a terrific talk.
Thank you.